Hi, everyone. Welcome to the NAGROM's seminar. It's a pleasure to introduce Professor Yanlai Chen from University of Massachusetts at Dartmouth. And Yanlai will talk today about the GPT-PINN, Generative Pre-trained Physics-Informed Neural Networks toward Non-Intrusive Meta-Learning of Parametric PDEs. Yanlai, please go ahead. Thank you.
Thank you. Thank you, Francisco and Maria and Bilgu and Tryon for organizing this nice seminar series and for inviting me to speak. So yes, I will talk about GPT-PINN. Hopefully by the end of the talk, I convince you the name is only partially artistic. So this is joint work with my student, Sean Kui, and supported by NSF and AFSR. So I decided to start by showing you the take-home message, and which is, I think GPT-PINN to PINN is what RBM is to FEM. And they're both what I'm calling structural preserving accelerations. So you have the finite element method for a single PDE in the parametric setting. We have the now well-known reduced basis method, and it preserves the structure in the sense that it keeps this, for example, the variational formulation. And in the same vein, we have PINN, physics-informed neural network. GPT-PINN accelerates PINN using the same structure, basically by its own game, so to speak. And so this is computing diagram. Not really computing diagram, but this diagram is what I'm hoping the take-home message here. And his outline, so I will start by giving a super brief primer of projection-based MOR, and then I'll move on to using one slide to talk about PINNs, physics-informed neural networks, and then talk about the design details of the GPT-PINN here. Finally, I'll show you some numerical results of us testing this recent result. So, as is well known, the PMO is for the so-called multi-query or real-time context, and in all these kind of situations, optimization, inverse problem, UQ, a sensitivity analysis. So we have a gazillion number of forward solver to call, and it's really not affordable to always call the forward model, the form. So we need to speed things up in this situation, and the idea of PMO is basically to build on top of traditional methods. Being a favorite method, find a difference element spectral. And in the linear reduction regime, this red, this is the answers. So what it does is it would pre-select some parameter values and call the traditional methods to generate those solutions, those N solutions. And once those are generated at any other parameter value, the solution would be approximated by a linear combination of those pre-computed solutions. And the traditional methods would have maybe a larger number of degrees freedom. Here I'm showing the mesh, and when it comes to the model reduction, each whole function would become one basis. I'm removing the mesh there, so that's one basis. So we have n degrees freedom, and in this picture we have 3 degrees freedom. And the task here becomes how we determine those C1 mu, C2 mu, C3 mu. That's what I'm calling this parameter to code. So the C1, C2, Cm are the code, the parameter to code map. What PMO does, the standard approach is it embeds physics. So here I'm using a quick slide to show that. So we have a PDE here and a simple reaction diffusion PDE in strong form, and we write it in weak form, nothing fancy. And finite element would discretize the space by, whatever you choose. And the bilinear linear form, basically numerical quadratures. And then you can solve. You have a discrete problem, all right? You have discrete problem here, the AH, FH. And we use KLM, standard notation in RPM to denote the dimension of the full-order model. And the reduced basis is in the same formulation. It's identical. It's just a change of space. You change from VH to WN, and this WN is n-dimensional. And for some problems anyway, this n is much smaller than the KLM. Thus giving potentially a speed up. There are a lot of details, which I'm not going into here, but the fact that it worked well depends on the so-called fast decay of the chromograph and widths. So here the sup inf would be the space, the distance of two spaces. I mean the manifold, solution manifold, and the n-dimensional space xn, and the outside infimum is you are looking for the best n-dimensional subspace for that purpose. So as long as we have fast decay in this quantity, which can be numerically checked, the projection-based approaches would tend to work well. So the one key thing to decide next is this space Wn, all right, Wn. And how do we construct that Wn? And there are a number of approaches here. I'm highlighting two of them. The first one is sort of the traditional RBM type approaches. So you have a posteriori error estimate, and which drives a greedy algorithm, all right? And it builds this space Wn from ground up. It adds a dimension 1 by 1. Is n, you get your n-dimensional space. And because of the greedy algorithm, so you ended up to construct Wn, you ended up only calling your form n times. That's one key feature of RBM. On the other hand, the traditional POD type of approaches, you do a sampling, a priori sampling of the mu domain, and then you perform SVD type of operations, you truncate it, and which means in the whole process, you usually solve more than, sometimes much more than n times for all the models. So I'm showing you this coordinate basically to show the amount of form data which goes from small to big when we go from greedy to pod. And on the other hand, there have been a lot of neural network type approaches to build this map, to build this parameter to code map. And some of them is not really easy because they don't really have a C. So I'm taking a simplistic approach here. Maybe some of these approaches are building from mu directly to the surrogate solution. So started from 2008 by Hashaven and colleagues, and there have been many papers. I'm only listing some of them, and again I'm being overly simplistic. Those are great methods they were able to train the map using targeted approaches with data generation and processing, a lot of really nice techniques. But for the three groups here, again with a simplistic summary, in the end, so whatever they do, they train the map. In the end, for a new mu, you give me new mu, I generate a surrogate solution. That step is done by a direct evaluation of neural networks. So you train it. In the process, you might have used a lot of physics and data, but in the end, you use purely data only. So you just evaluate your map, your trained neural network for any new mu. And I want to highlight a very nice analysis paper in 2022 by this group, and they provide a theoretic upper bound on the complexity of DNN, the deep neural network, approximating parametric solution maps. So roughly speaking, maybe in one line, one sentence, so what they kind of showed is that, whenever RB, the P mode would work, you could build a DNN, and there exists such a DNN, and they give an upper bound to the complexity of the DNN. The size of the DNN would be cubic with respect to the dimension of the unit basis space. That is not constructive though, so they prove the existence. So that's the neural network type of approach. So I'm trying to catalog these methods using the horizontal directions, amount of data, the vertical directions, amount of physics. So RB and the pod, I would say, is on top. So in terms of amount of physics, because whenever you have a new mu to calculate the surrogate, you in that step, you're building physics. And on the other hand, the neural network regression type approaches, they don't. So that's on the fourth quadrant. And you tend to use more data, just like POD. Speaking of neural network, so there's a little known method called PINN. By which I mean pretty much 90% of people knows. Here, the idea is that you build a neural network and WB. So here W are the weights, B are the biases, and it goes from XT to U, right, to U. So it's with a number of hidden layers, and those are a affine operation, the CKZ, composed with a nonlinear guide with nonlinear activation function sigma. So the sigma is a standard nonlinear activation ReLU type. And basically you're guessing your solution, right? You parameterize your solution by this neural network. That's the idea. And you have a lot of parameters here. I'm calling all of them by theta. Okay, all those hidden layer, the weights and biases, I call them by theta. And basically, your solution is parameterized by this theta. And then you train your network by optimizing by minimizing this mean square error. So mean square error is right here. So that's where you calculate the residual, right? Residual from your PDE if you use your current neural network, all right? And then you calculate also the mismatch between your current network and the boundary condition, initial condition. That's the first MSE is about with UPCIC. And you add them together and you minimize it. You train your network, you find the theta star, right? Oh, that's where the magic comes in, the automatic differentiation and the basically chain rule, the backpropagation. The gradient-based approaches that come in to find a theta star that give you, a minimum that you can accept, not really a global minimum, of course. So once you are satisfied with some kind of, MSE value, you convert with your theta star. I'm calling this guy, this total, this per c, right? This per c is a whole composed nonlinear many layers function. Then I'm going to use that as approximation of my U, of my PDE solution. That's it. So that's the basic idea of PINN. Well, so then comes the, just like a finite element, this is for one solvable for one particular PDE instance, all right? So as customer in this community, we tend to ask, well, what do we do for parametric setting or multi-query real-time setting? What can we do? All right. So there's a lot of challenges. One challenge is that this theta, this WB, the weights and biases, because of the number of hidden layers and the width of each layer. So this theta tends to be high dimension. So just like we all know, the ChatGPT, GPT-4, right? They use a huge number of parameters, so tend to over-parameterize, including in many of the developed PINNs. And the training takes time. And if you want to query your PINN many times, of course, things adds up pretty quickly. So it quickly becomes, unaffordable. And another observation that we've had is this data, if you think of this data as if your parameter is a mu again, your theta is a function of mu, you don't really have a low rank structure in that theta. So the traditional kind of technique, well known in the community, we cannot really leverage them. You cannot find a low dimensional structure in this data. So what do we do? There have been a few, many actually, especially the last few years, there have been many papers coming out attempting to kind of do this. In fact, there are many of the great papers, of course, and I'm hearing a whooshing sound of another paper coming out with now. So the first type, what I'm calling PINN plus X. So they're trying to explore the mu dependence. Okay, so if you have enough data, you have mu and your theta. Basically, you can do regression, statistical regression, or traditional interpolation. You use RBF to build this map, and then with the new mu, you can just evaluate your map. And they also worked on the standard meta learning type approaches. ML, and LEAP. And the second that I'm highlighting here is DeepNet and FNO. And they are based on POD type of thinking. So basically, you are sampling your input function space. So if your input function is your source term and it's in some kind of polynomial space, you sample that. And then it's also data driven. So in the end, you evaluate your map. And the recent paper is Meta NO by this group. So the idea over there is they take the parametric dependence, they capture the parametric dependence on the first layer, and for all the other layers, they share the same structure. So which means once you do one of them for one mu, you can transfer all the theta mu for the other layers, which saves time. And still in the end, the surrogate is data driven. And the last one I'm highlighting here is the so-called PRNN by 2 years ago by Hanshaven and colleagues. R is for reinforced, so physics reinforced neural networks, and they ended up needing less data. And this mu T to C mu in the end is still regression based. They to train the map, they bring in the physics to explicitly by building the residual, so which allowed them to cut down on the amount of data needed to train the map. So that's called PRMN. Again, I'm trying to catalog these methods using amount of data and amount of physics. I would put all but PRNN in the big data and less physics quadrant. And the PRNN is on the third one, it takes less data. So the question is, what do we do in the second one, right? Which is perhaps a more preferred approach. You have physics, but you don't rely on a lot of data. And that's what I'm trying to argue. GPT-PINN is right there, kind of like where I placed RBM in the same system. So what is GPT-PINN? And I'm showing you here a simple slide to try to explain the inspiration. And here is the RBM answers, right? So we have this summation CI U mu I. And of course, now when you use PINN, we use PINN, the U, the purplish U becomes this per C NN, right? This is a neural network function, theta I. And if you think about it, this summation is nothing but a simple one layer, zero bias, typical neural network operation, right? You multiply per C with your C. C is like your weight, per C is like your activation function. So that's the idea. And this N is basically the width of the hidden layer. So this whole sum shows that we only have one hidden layer. And this blue N is the width of that hidden layer. And just like RB, we increase this N in the greedy process. So here we grow this hidden layer. So we have one hidden layer. We input layer, you have X and T, output layer is U. So it's 2, N1, all right? And if depending on your X, if your X is a multi-dimension, it's more than 2. But for 1D, let's say, it's 2 as a 2N1 simple network, which I'm denoting by NNR. I will keep using that notation. And the N in the middle, the blue N is the width of the hidden layer again. And the cyan C's are basically the weight at the ith node in this hidden layer. And the magenta per C, right, is this customized activation function. So different from the typical PINN where you use ReLU or the hypertangent and so on and so forth. So here you cannot use any of them by the answers. The theory tells us we have to use a full PINN, right? So that's the idea. So it's well chosen pre-trained, but they are pre-trained. So we just need to evaluate. Evaluation is cheap. Training is expensive. Once we are done with pre-training, the evaluation is very efficient. So that's the idea. And here is the schematics. We have this one hidden layer here, all right? And you see each of them, each node is a full PINN. And then we have the C's. The C's are the weights, all right? You multiply them, you form your U. And now for any, I'm calling prompt, for any prompt mu, all right? And you have a PDE, so you have your governing equation, you have the boundary condition, the initial condition, potential, they can all vary with the mu. And you do your pre-computation just like RB, and you can calculate your loss, right? With the current C's, with the current guess, your C, all right? So this MSE, the same notation as a traditional PINN. MSE for the boundary condition, initial condition, and the PD residual, all right? Adding together, and I'm denoting the whole thing because it's function of C, all right? C is function of mu. So this is L GPT-PINN sub PINN sup GPT of C mu. So this whole thing is a function of C, and you train it. Okay, you do, this is you don't even need to the backpropagation because it's one layer. It just simply calculates gradient. You do a gradient descent. You're done. So that's the idea. And I'm showing you here some features here. So this is the training. This is the training. All right, we calculate the gradient. We have the learning rate, little delta. You train your C. And of course, now with any prompt mu, we do embed physics because this loss has to be residual built in. It's not a simple evaluation of a map. And we need small data because we just need those N nodes and neurons. We just need those M pins. We never train more pins than those. And the neurons are the meta neurons, super neurons, so to speak. Those are adaptively built and customized for the problem at hand. Those are a particular pin at a specific parameter value. Sorry for the little bit of noise here. And it is non-intrusive. Basically, as we will show, I will explain in one of the examples, you can plug in any existing pin into those neurons. Because the outside, that's 2N1, the NR 2N1, that network is independent of those pins inside the neuron. they don't really, the meta network doesn't really see the pin structure inside. So in that sense, it's totally non-intrusive. In fact, I'll show from one example. We just take a specially designed pin. We don't really worry about what's inside. We can use it and for our purpose to get great result. So it's non-intrusive, and it accelerates pin. We've observed 2 to 3 orders of magnitude speed up. Of course, with the investment, after investment state is a marginal speed up, but I'll tell you, in the simple implementation, how much investment you need to gain on your investment here. So some delicacies that I want to highlight here. One is just like RB and POD, precomputations are key. Whenever you can pre-compute for parts training. So inside here is I want to point out, the derivative is basically linear, and the pins you calculate the residual at a bunch of points. That is collocation in nature. Okay, so which allows you to pre-compute things. So whenever I have a theta I calculated, I convert on the theta I at i's neuron, I calculate the value, the KLC are the collocation sets, online collocation sets for the residual boundary initial conditions. So I calculate, all the points that you are going to use later on. I pre-calculate those values and the derivatives, the time and space derivatives. I store them. Okay. This can be small, by the way. So once you have those, the training can be very efficient. And the last piece is an error indicator. And here's a review of RPM, a posteriori errors estimators. So it helps to generate the reduced solution space. It certifies the accuracy, and as is well known, it's often residual based. And we were like, what we can do here, and there's aha moment in one of those boring Saturday morning runs. All right, hey, here the loss is residual based, so let's just use the loss, the terminal loss of the. You train your reduced network, you have a loss. The loss includes the residual in it. So that's also residual based. Of course, it's not a rigorous error bound, but it's enough, turns out to be a very efficient error indicator. And again, it is residual based. So now we can describe this greedy algorithm. So we have a mu training set, okay, C train. And you have a full pin for your problem. And this is typical RB type of greedy algorithm. I select my mu1 randomly. I set up basically empty GPT-PINN. And now you have your n is 1, you have a mu1. So I train my pin at that mu1. So now I update my GPT-PINN. I get a GPT-PINN of 2 and 1. In the beginning, just 2, 1, 1. All right. 2, 1, 1, you train your 2, 1, 1 everywhere. You discretize the parameter domain. You record the terminal loss, okay? And just like RB, is this loss less than the tolerance? In the beginning, of course, is a super small network, so likely it's not. So you look for where is the maximum. So where if you use your current meta network, you are doing the worst job at that mu, right? So that's your enemy. By including this, you turn the enemy into a friend, and you take that as your next mu, all right, next mu, and you repeat, right? You keep doing that, and at some point you stop. Either the lesser tolerance, or maybe you can only afford to use this many neurons. You stop at that point. And so that's it. That finishes the description of the GPT-PINN. Now I'm showing you some results. We tested on 3 problems. The Klein-Gordon equation here, I'm denoting by KG, and Burger's equation, and Alan Kahn. with 3 and 1 and 2 parameters. And here is a setup for the PINN and the GPT-PINN. And I'm basically showing you the architecture of the full PINN, a number of intermediate layers. The outcome turns out to be very tricky to use PINN to solve. There's have been many papers, and it's here that I was talking about, to highlight the non-intrusiveness. We use a self-adaptive PINN developed in the literature, and it's a fairly large in the PDE setting anyway, a large network. And all fully connected with the given activation function, and these are the collocation sets for the full PINN, and the optimizers and the learning rate, and the maximum epoch is 60, 70, 20 thousand. And I'm listing the C train. So I'm highlighting by red the GPT-PINN setup. The learning rate is noticeably larger than the full PINN, and the number of GPT-PINN epochs is much smaller than the full PINN. And a little bit more details for the burgers. When the viscosity is very low, we have basically a shock forming at a later time. So in that case, because of, again, the residual is collocation in nature, so the derivatives are not really reliable, right? Because they're close to the shock. So a simple strategy that we took was we excluded the top 20% of the points where the derivatives are the largest derivatives. A little bit of pruning going on there. So for the result for the KG equation, here I'm showing you on the top left is the parameter values, and then the middle and the top left, top right, the GPT training losses. So the middle is a worst case scenario. The right is all those statistics, and you can see that they are pretty cleanly exponential. And here the black is a GPT-PINN. These are so-called adaptive neurons, right? And for comparison, we're showing you this uniform neuron. By uniform, we meant we just sample according to some priori rule, uniformly same number of neurons in the parameter domain. This red. This is also doing very, very well, right? By using 15 neurons, we get a 3-digit in the loss, and the fact that you can do it by just doing uniform neurons shows the power of the idea of using a full PINN at one node as a customized activation function. And the bottom row is a first 3 PINN solutions the GPT-PINN adopts as activation functions. Just to give some idea. The testing, so we tested another set of parameter values not included in the training, and we get this is 2 digits, 0.02 basically for the GPT-PINN, the error. And I want to highlight this third picture here, which I'm showing you is a cumulative runtime, right? So you run the full PINN, for up to 200 times. Of course, it starts from 0. The slope is simply the time for each PINN, and then you run the GPT-PINN, all right? You run the GPT-PINN, the black one, because the training will take some time in the beginning. Once you're done with the training, each run takes negligible amount of time to train the seeds. So the ratio of the slope is basically the speed up. It's 454 here for this implementation. And the intersection point is, of course, where it's worthwhile to invest, right? So how many runs does it take? Is maybe 25, 24. It's worthwhile. How many queries would it be worthwhile? Now, one more slide for KG. Here is I'm showing you the loss, the PINN loss as a function of the epoch, right? All the way to 75,000. And just like a typical PINN training, it goes down, but there's some bumps. This is not less so for other PINNs. It can be much more dramatic, the amount of oscillations. And for the GPT-PINN, it's up to 5,000 here. It's smoother. It's noticeably smoother than the full PINN, and the ones in the middle are just the pointwise error. And I'm moving on to the second example, the Borges equation. So here the parameter distribution is clearer in terms of its distribution. We started in the middle, right? And you can see, 2, 3 goes right to the boundary, just like RB, right? From RB training, we see this kind of behavior. 4, 5, 6 towards this end, and then you pick a few in the middle. So it's a typical RB type of behavior. And again, the loss versus neurons is exponential. And I'm showing you the three guys here, 3 full PINN solutions, the 3 activation functions. And for testing for Borges, it converts again 2 digits, all right, with only 9 neurons. It's a much smaller network than the full PINN. And the cumulative runtime on the right is the slope ratio is 111, and the intersection point is what's that, 12, somewhere between 12 and 13. That from where it will be worthwhile to invest. And again, the same picture in terms of the loss as a function of the epoch, and similar observation as a fourth example. Finally, the Allen-Klein equation. Again, Allen-Klein is challenging for PINNs. So we took the self-adaptive PINN by McClellan and Braganato, developed in 2020, and it's a specially designed PINN. I just put it that way. There's adaptivity built in, and we simply use it, and it's greedy. Whenever we need to train a new PINN, we call this SA PINN, right? We build our GPT-PINN, and you see this distribution of the parameters selected by the GPT-PINN, and again, the largest loss here is at right below 0.01, so 3 digits, and this converges nicely. The below pictures are the SA PINN solutions that GPT-PINN is adopting as activation. And we test it. For this, we also need to run to 9, and it's doing reasonably well with up to 9 neurons. And in terms of cumulative runtime, so this one, because of the SA PINN is more complicated than the vanilla PINN, so the speed up is more dramatic. But the GPT-PINN is more than almost 2,000, 1,600. And I want to point out that just like a traditional PMO, so the minimum amount of this intersection is your number of bases, right? The number of neurons, because you need to call your full PINN 9 times. So it cannot be lower than 9, and all those additional costs would make this a little bit more than 9. And we're getting very close here. It's very it shows the efficiency of the GPT-PINN, where it's below 10, slightly more than 9 for this example. You really cannot do better than 9. So this can be very efficiently done in the parametric setting, using build on top of a PINN that works for your problem. And for this one, again, it's a little bit challenging. So the training takes 2 phases for the full PINN. we use Atom, and then we use the standard LBF GLs for the second phase, and we're able to get to 3 digits in terms of loss, and the GPT-PINN is a bit smoother again, and here is just in the middle the error distribution for between for the GPT-PINN. All right, to conclude, so basically we designed, to the best of our knowledge, is the first PINN accelerator, the first perhaps structure preserving accelerator, right? So we can accelerate the PINN by using the PINN structure, using its own gain, which is really just mimicking the RBM framework. So it's like the RBM for PINNs. This framework can preserve the PINN structure and the physics conforming property has physics built in, even online. It's not an evaluation of the neural network. It relies on minimum amount of form data, and it's non-intrusive, make it portable. You can plug in the pins. And it adopts for PINN, single neuron, and we use a loss to guide the grid construction. This one layer neural network is adaptively built from ground up, from 1 neuron, 2 neuron, all the way to n neurons. And it naturally features offline online decomposition, leading to a practical speed up as shown. So this is my email address, and again, I want to acknowledge funding support from SF and AFOSR, and also want to give a shout out to our campus. In Masdalimos, we have a master program developed by Dr. Ram Bala that benefits the campus a lot. And CSCDR is for our computing center, Center for Scientific Computing and Data Science Research. It's a second home to a lot of researchers. In terms of paper and the code, you just Google GPT-PINN. It's right on top. The paper and the code is open source. Feel free to let us know with any questions. Hopefully nothing is missing, but if anything, email us. We'll make sure to get to you. But yeah, people tested seem to be working well. All right, that's it. Thank you so much for your attention.
Very nice. Thank you. Thank you, Yanlai, for a very nice talk. Very clear, informative, some new ideas, and thank you.
Thank you so much. Thank you for the nice words.
Any questions from the audience? I have a few, but maybe somebody from the audience would like to start first. I cannot see. You can unmute yourself or just raise your hand. I don't know. Okay, maybe I can start. So the first question. I really liked it. I really like this connection between RBM, so connection to RBM. I think that this is very nice. And Yanlai, so the question I have is, so you made the point that in RBM you use residual-based error indicators, and then you said that we use the residual in our framework as well. So this is similar.
Yeah.
But you don't have. Do you have rigorous bounds? I mean, what can you prove about the neural networks in general, and then the
yeah. Yes, of course, a great question, right? A very important question. No, the simple answer is no. We simply take that loss. That is a residual base. It's a loss that only has a loss value, right? So just like, wait, what am I? No. So yeah, it's just this, right? There's no scaling with stability. No, it's not rigorous. But that's why we cannot call it error estimator. In terms of error analysis for PINN, there's a couple of papers out recently. I don't know very well to make remarks on them. I don't think they are as rigorous as the traditional finite element type of analysis. But there have been analysis, and there's quite some work in terms of expressivity of DNN, not just PINNs, right? There'll be some work like that. So yeah, it'd be nice if we can refine this error estimator, right, to make it rigorous. And this is the first step to simply, just use it, take it, and do it.
Fair enough. Fair enough. Thank you. Any other questions for Yanlai?
Can you hear me?
Yes. Go ahead.
Yeah. So Yanlai, beautiful presentation, and
thank you.
Particularly to a person who's kind of even new to these ideas. Very clear. I learned a lot. Just a quick question. So there is, if where do you anticipate the overhead, right?
Yeah.
Meaning, at your zero, right? When you have the overhead, if you go to slide 25.
Yeah, the overhead, I'll show you 25 soon, right? But the overhead would be, well, by overhead, I'm assuming you was on top of those n pins, right? So every time, so this is the basic, the time for your full pin. Once you do your full pin, you would have to I'm not listing them here. So, well, I can point to here, right? You have to train your GPT-PINN. So in the beginning, you have a 2-1-1 network. You have to run your small network everywhere at all the mills here, all these mills.
Yeah.
Those are the overhead.
Yeah.
Yeah. Those are actually the biggest overhead, right? That's elephant in the room.
Exactly. So my question was, what are the cases where you anticipate this overhead, if any, right? If there's any case where you anticipate this overhead to become a challenge, meaning the overhead is so large, right?
Yeah.
I mean, I'm just thinking out loud. Are there cases where you can say, well, you know what, if I go this route, the overhead is so large, right? Or maybe no, maybe there is no case, and typically the overhead is small, and you quickly, get to a level of accuracy. You know what I mean? I mean,
I mean, this overhead is would be somewhat determined, right, by the size of your training, the parameter training set. This Cassie trained, in a setting when your parameter is super high dimension, that would be the case that it's really not affordable to keep running this small problem over and over, right? We run 2-1-1, we run 2-2-1 all over the place, and 2-3-1, 2-4-1, just like a standard greedy for RB. Each of them is super quick. But if your Cassie train, if it's a high dimensional parametric problem, you need to run this 2-1-1 a gazillion times. That takes time.
Yes.
Yeah. So that will be a example. Yeah.
But I mean, the typical PINN, right? The typical PINN, again, this might be naive coming from me, who doesn't know much of this stuff. The typical PINN has the same issues, right? So if you have a very high dimensional problem, so the typical PINN does well. I mean, it has no issues. Is that what the case is?
Well, good point. Very good point. Thank you. I mean, the typical PINN is for one problem, right? You have a huge parametric problem, but if you want to train it at the same number of locations in your parameter domain, of course, the typical PINN would have a hard time, right? Because this straight line that directly scaled with the number of runs, right? So of course, the typical PINN would suffer. Yeah. So even in the low dimension, even the parameter is low dimension, typical PINN would suffer as long as it's multi-query.
Exactly. Got it. Thanks for that. Thanks very much.
Thank you.
Any other questions for Yanlai? Maybe I can ask one final question.
Yeah.
So on slide 23, you're talking about Burger's equation, and so then you're talking about like small new values for Burgers. So I was wondering, actually, this is more of a general type of question. So whether you have any experience with chaotic type of problems. So how would neural networks, PINNs, and fare for problems where you have chaos? I'm thinking about
I mean, I guess, short answer is no, right? I don't have much experience there. But I mean, I would say, I guess one remark I could make, maybe at least related, if the chaos is not moving around with your parameter, then it's fine, right? Just like the example that I showed at the beginning, we have a degeneracy in the solution, and in the case, if it moves, if the comorbid width is reasonably decaying, I guess, you could play this game, this removing of maybe the chaotic regime, right? What do we had from what do we call with Yvonne, Sika, and others, and Li Jie, reduce overcollocation, where we're kind of basically doing a very sparse collocation. So because in the end you only use n bases, you don't really need 10,000 points. Ideally, you can go down to 10. If you have 10 bases, you use 10 points. So what I'm trying to say, is that perhaps it's a wild guess. Perhaps you can cut down a lot, which actually I'm pretty sure you can cut down a lot. So how to really to the bare minimum or not, that's a different question. But perhaps for the chaotic region, you can cut all of them off, and as long as you have reasonable number of points left, because again the neural network is much reduced. That's a very wild, likely inaccurate remark. We are working toward that direction, actually, to see how that goes. Yeah.
This is very good. I mean, and this is a tough question. I think that in general, this is a tough question. And our experience with data-driven modeling has been for, providing correction terms. And our experience has been that for challenging flows, so data is very useful if the flows are, if the system is well behaved. As you said, if there's some hope. But if you think about like a wild system, so in our experience, data-driven modeling by itself was not super successful. What was successful was to supplement it, maybe like you're doing with physics. And this combination for us seemed to actually work well. So I agree with what you said. It's not an easy, there's no real answer, but okay, very good. Thank you.
Yeah. Some physics, some nonlinear reduction, right? And
exactly.
Yeah.
Okay, very good. Any other questions for Yanlai? Well, if not, let's give him another round of applause, and thank you so much.
Thank you, everyone. Thank you for
that was a great talk. All right, very good. All right. Well, this concludes our seminar, and we'll see everyone next Tuesday. The announcement is gonna come up as usual on Thursday. Thank you. See ya.
Take care.